Morning, good afternoon, or good evening, whatever time you're watching this educational video. This is part two of Coulomb's law sample problems. Let's go ahead. First problem will be a pair of point charges. Charge 1 and charge 2 are 4 times 10 raised to negative 6 coulombs and 5 times 10 raised to negative 6 coulombs respectively. They are placed at 0.30 meter apart in a vacuum. The recorded coulombs force between them equates to 1.7 Newton. Figure out the epsilon naught of the system. We will be explaining more about the epsilon naught and how we will interpret the magnitude it will be calculated. Okay. Once we calculated epsilon naught, what does it mean? Okay. In our problem, we have the values of our charges here. Both are positive charges. Okay. So they will gonna be repelling. And the Coulomb's force, as they repel, it's equivalent to 1.7 newtons. And the distance between these two charges are, the distance is 0.30 meters. We will be using the Coulomb's equation, but this time we will unpack the Coulomb's constant because we need to figure out the epsilon naught. So we need to have a variable of epsilon naught in our problem. But in this case, we cannot see it. So we need to unpack Coulomb's constant here. Coulomb's constant is related to the epsilon naught. As you can still recall, constant or the Coulomb's constant is equal to 1 over 4 pi epsilon naught. So we have the variable epsilon naught here. We will gonna isolate it later on. And we will substitute this k, the value of k, this 1 over 4 pi epsilon naught, to our equation in Coulomb's equation. Okay, instead of writing k, we will change it to 1 over 4 pi epsilon naught. As you can see, instead of writing k, we substitute the value of k, that's 1 over 4 pi epsilon naught, because our target is to figure out the epsilon naught. We will isolate it later. The next thing we will do is to multiply numerator to numerator and denominator to denominator, and we can simplify it in this way. Next thing is we will do multiplication. So we will cross multiply 4s and the variable the variables 4 pi epsilon naught r squared and 1 multiplied by the product of the charges. So we can have this new equation now. Next, we will isolate the epsilon naught. We will gonna retain the epsilon naught on this side of the equation by dividing both equation by force 4 pi r squared. Force 4 pi r squared. We can cancel 4 pi r, 4 pi r, and the radius. And if you notice, we retain the epsilon naught because that's the target. So we can have this formula, the formula to figure out the permittivity of free space. Okay. And if you will plug all the given variables perfectly, so you can have it here. This is the value of charge 1, value of charge 2. We will get the absolute value of this uh, charges, but anyways, both are positive, so no problem. And then you will have the value of force 1.7, or the value of pi 3.14, and the distance between them it's 0.30 meter. Then don't forget to square it out. And the answer will be 4.16 times 10 raised to negative 11 Coulomb squared per Newton meter squared. By the way, this Coulomb squared over Newton meter squared, this is the other way to write the farad per meter unit. That's the unit of the epsilon naught. Okay. So instead of writing F over M or farad per meter, you can also do it this way. Coulomb squared per Newton meter squared. The epsilon naught, how we interpret it after we calculated the epsilon naught. The North Stars, it tells how much the vacuum opposes or permits the electric field created by charges. So we have charges creating the electric field, and then when you will expose this electric fields to a vacuum, the vacuum will oppose or will permit this electric field. It tells how easily those field lines can spread in free space. So that's another concern here for the epsilon naught. It will tell us how the electric field can easily spread or difficult to be spread. Okay. Low permittivity or low permittivity means that the fields will spread easily and the force is strong. Meanwhile, high permittivity means the field is spread poorly because the force is weak. It it is supported by this formula. If you can see, it's inversely proportional. If you will have low epsilon naught, low permittivity, the force will be strong. So you will have high magnitude of Newton. On the other hand, if you will have high permittivity, epsilon naught will be going high, the force will become weaker, and the field will have a hard time to spread. So the force will gonna be weaker. It's inversely proportional, and I hope you get it right. The vacuum, the epsilon naught in a vacuum, this is the threshold. It's 8.85 times 10 raised to negative 12 Coulomb squared per Newton meter squared, or the Farad per meter. And this is very small, so if it has a low permittivity, the force there is strong. So it has a relatively strong Coulomb's force. If we will compare our answer earlier, as we calculated the epsilon naught of the isolated charges in a vacuum earlier, if we will compare, obviously the value of epsilon naught in our isolated system earlier is greater than the vacuum's epsilon naught value. So in this case, the epsilon naught is greater than the vacuum. So we have higher epsilon naught. So we will have weaker interaction or weaker electric forces or Coulomb's law. Okay, now let's have this problem. We have the x-axis of our Cartesian plane, and we have these three charges isolated in air with a relative permittivity or E epsilon R of 1.0006. No unit, it's a dimensionless variable. Okay. Relative permittivity or epsilon R, no unit. And remember, uh, these charges are in air, not in vacuum. So our Coulomb's constant or K is not anymore 8.99 times 10 raised to 9. It's going to be different. We will be calculating the Coulomb's constant in air, not in vacuum, provided that we have the relative permittivity, which is 1.006. We can use this magnitude in our calculations later. So these are charges like charge 3, that's the value, charge 1, that's the value also, and charge 2, that's the value. And then the distance between charge 3 and charge 1, I have a mistake on this. It must be 3 because I already prepared the solution and I used 3 meters instead of 4. So we will change it right away. And we have the unknown radius or distance between charge 1 and charge 2. Our task is to figure out the distance between charge 1 and 2 if the force is 0.05. So the Coulomb's force is already provided between the interaction of charge 1 and charge 2. The next task is figure out the net force exerted on charge 1, and this will gonna be our main character or our point charge in this system or in this problem. We will try to find out the interaction between Q1 and Q3, as well as Q1 and Q2. Okay, let's begin. Figure out the distance between charge 1 and charge 2 if the force is 0.05. So it's provided already. The interaction between force on charge 1 due to charge 2. Okay, so charge 1 is our reference point, and charge 2 will have to do something to charge 1. So in this case, charge 2 is negative by the presence of a negative sign here, so it's negative. And charge 1 is positive, therefore it will gonna pull charge 1 towards it. It's going to the left. Okay. Before we will calculate everything, we will try to find out the Coulomb's constant in air because our problem, the charges are in air. To calculate K in air, we will have this shortcut formula if we want to know the Coulomb's constant in specific medium. So the medium is air. All you have to do is to divide the constant in a vacuum over the relative permittivity. In the problem, it's provided. Thankfully, it's provided. So we can just plug in 1.0006 to our epsilon r here. So by that, the value of your K in a vacuum, it's 8.99. We discussed this one in our previous video. It's 8.99 times 10 raised to 9 Newton meter squared per Coulomb squared. That's the constant magnitude if the charges are in vacuum. Okay, we will divide it by the relative permittivity. So we can have the quotient of this very long number, and we can just convert it to scientific notation. So we can have this 8.98 times 9 times 10 raised to 9 Newton meter squared per Coulomb squared. We will use this value in our Coulomb's equation here because the charges are in air, not in a vacuum. So we will substitute it, but in this case, we will derive the formula to get the R because our task is to figure out the distance or the R between charge 1 and charge 2. So in my previous video, I derive this formula here, this one, from our Coulomb's equation. So you can just watch it again if you like. So we will now substitute all the needed variables or the needed magnitudes to our variables. So we can put it this way. So the K, it's the value of K in a vacuum. This one, we calculated it earlier, seconds ago. And then this is the value of charge 1, charge 2, and this is the force between them. Do not worry about the negative sign of charge 2 because at the end of the calculation, we will have the absolute value of these charges, the product of these charges. So when you will plug all these magnitudes in your calculator, so it will generate this answer 0.3592 meters squared, and we will get the square root, the positive root of this magnitude. So we can have this long and small numbers. Meter squared will be cancelled because yeah, we square it out. Then we can convert it into scientific notation so we can have this figure here. It's rounded off, so it becomes 6.0 times 10 raised to negative 1 meter. That's the distance between these two charges, 1 and another task is to figure out the net force exerted on charge 1. So this is going to be our main character again, charge 1, and we will gonna know what will be the total net force between charge 2 and charge 1, as well as charge 1 interaction with charge 3. So we will add the forces. We need to find the Coulomb's force of charge 1 and 3 because charge 1 and 2 it's provided already in the previous task. Since force on charge 1 due to charge 2, this one, charge 1 due to charge 2, it's provided already. It's 0.05 newtons. So we need to figure out the force on charge 1, again, our point charge, to the other charge nearby. It's charge 3. So we need to find the Coulomb's force between charge 1 and 3. So remember, it's in air. The charges are in air, so we're gonna use the Coulomb's constant in air as we calculated minutes ago. So we will be using the Coulomb's equation again, and then we will substitute the units perfectly. So this is going to be the Coulomb's constant in air. This is going to be the value of charge 1. And this is going to be the value of charge 3. It's negative 3 times 10 raised to negative 6 coulombs. Don't mind with the negative sign here, because at the end of the calculation, we will just get the absolute value of the product of these charges divided by 3. That's why we will going to change 4 here to 3. My apology. And don't forget to square it out. Plug these magnitudes to your calculator. It will give you this magnitude. Now we have the Coulomb's force between charge 1 and 3. We will just get the net force. But before that, we should be mindful with the direction. So let's begin with force on charge 1 to charge 2. What's the direction? Force on 1, and we had charge 2 here. Charge 2 is negative, charge 1 is positive. So the direction will be this way. Charge 2 will pull the positive towards it. That's force on charge 1 to charge 2. Meanwhile, force on charge 1 to 3. Charge 1 is positive, charge 2 is negative. So, charge 3 is negative. So, charge 3 will have to pull the positive charge 1 towards it. So, the direction will be going to the left. In this case, we will make it negative here. As you notice, I pulled it out, I highlighted it. So, it's negative now. It's just the direction, okay? Now we will plug in the values. In force on charge 1 to charge 2, in the previous task, it's 0.05 newtons it's given. And we calculated a while ago 2.99 times 10 raised to negative 3 Newton, but this time we have negative sign here to represent the direction. You will do the math and it will give you these values here. You can have it this way. It's 0.04701 Newton, and that's the right to the right. Or you can have the scientific notation, 4.7 times 10 raised to negative 2 newtons to Newton to the right. Okay. I hope you learned something from our video for this moment, and I hope it will help you in your review. And yeah, see you around until next time. Don't forget to like or comment or subscribe to this thing so that I will be motivated to do more of this. Thank you so much and see you around until next time. Bye for now.